Now, following my own, and I'm following thread 1 just now, program verification, because the next stage in this for me was actually stimulated by the very lectures that Joe Stoy has talked about, Dana Scott's lectures, which I went to when I was in Swansea, drove across to Oxford, which then seemed to be quite a long way, but now it's no deal. And this was new and exciting stuff to me. I really didn't understand it very well, but it seemed that the very kind of thing, the understanding that I was wanting to get, was coming about via these domains, which Scott was producing. I actually was very moved by the hierarchy of domains, which Dana Scott said was no good in the end, and withdrew, because what seemed to me very important was that we should understand our programming in terms of hierarchies of more or less complex things. A first order function is much simpler than a second order one, and so on. So you need that hierarchy there, whether or not, as Scott proved that they could all be squashed down into one amazingly uniform whole. Nonetheless, you wanted that hierarchy. So I was very happy with that hierarchy. Well, the next stage in my story was that I arrived in Stanford to work for John McCarthy. Actually, I don't know why I went there, except that it seemed an exciting thing to do. So I went to work for John McCarthy, who was not the most talkative of people. But anyway, I sat around wondering what to do, and it seemed that they very much needed to impress Alpha at the time. Most people were very much interested in artificial intelligence and that sort of thing. What there wasn't was a really a piece of rigorous implementation around the place. So I said, I'll design a theorem prover based on Scott's logic. Now, I said Scott's logic because actually Dana Scott had enshrined or explained his type, the OY icewind thing. He had explained it in a logic. And that logic, it was a natural deduction, a very simple logic, and I could see how to implement that. And I could also see that you could express in that logic both the syntax of a programming language and its semantics. So I thought, isn't that the way to do program verification? Let's not do it in terms of axioms or whatever. Let's do it via the semantic understanding of the language in terms of abstract objects. Well, actually, that turned out to be not the right thing to do, but it led me in some interesting directions. At least it wasn't the right thing to do if you wanted to verify the factorial program. It was a very complicated thing to do. But what I did was to implement Scott's logic, and I did it in a way in which turned out in the end to be, I think, reasonably important, which was there were various paradigms about how to put logic onto a machine at the time. There was Alan Robinson, resolution theorem proving, automatic theorem proving of other kinds. At one end of the spectrum, the computer will do it all for you. At the other end of the spectrum, there was an amazingly expert and visionary piece of work by Bruijn I think it should be pronounced, called Automath, on proof checking, on how a human could organize their material with the machine in such a way that the machine would verify every step of a proof. Now this is an extraordinary extremal position. You had at one end the automatic theorem proving, at the other the totally unassisted job, except from the point of view that it provided structure for you. Or De Bruijn's theories were called books, in fact. You would write books in his proof check. So what was there in between? Because clearly, when we want to verify programs, whatever they are, we want human assistance there. We know the automatic theorem prover isn't going to work. So we need assistance somehow. And so what kind of a dialogue is that going to be? And this notion of there being, as it were, a goal-seeking dialogue between human and computer became at the front of my mind for a long time. The interesting thing was, apart from that methodology, which I'll come back to a bit in a moment, that it turned out that proving programs is pretty hard, but proving compilers is easy by comparison. The reason is that the semantics of a compiler has nothing to do with any object domain, any application domain. It's simply to do with programs. So somehow it's all much more in-house, if you like. It's stuff which we understand. It's computer science. It's syntax and it's semantics. So you would express the semantics of a source language in Strachey's semantics, Strachey-Scott semantics. You would express the syntax in that way for both the source and the target. You would write the compiler, translator, simple program. You would write that in the logic, and then you would be able to formulate and prove the very simple statement that you have a commuting diagram. You translate and execute, or you execute and translate. And that commuting diagram was simply the expression of the correctness of the compiler. And so, and by the way, I mean, this was built on McCarthy's previous experience of proving a bit of a compiler, albeit without loops, for a language without loops, with one of his students. So he'd done that in first order logic. I think I demonstrated that Scott's domain theory there and the logic on top of it was actually a very good vehicle for doing that. So that work on compilers, it showed me not only that, that you could do compilers if they were simple enough, but also that the methodology of proof of systems, or machine-assisted formal reasoning, as we called it, that possibly had some mileage in it. Out of that case study, what came the idea that we actually want to get a bit clearer about what kind of dialogue this is. It's a kind of goal-seeking dialogue, so we want to express goals, expressions to be proved. Obviously, we want to express what theorems are. We want to express proof strategies, ways of going about a proof. We want to be able to say to the machine, why don't you try that strategy? So we experimented with strategies. I remember one day, since we were allowed to be anecdotal, I think that's been accepted. I was working in a very simple theory, the theory of substitutions. Well, substitutions actually aren't that simple. I mean, there's anybody who's tried to formalize them and prove theorems, particularly false ones, about substitution, which everyone will know. But in any case, I was working with the theory of substitutions, and I had a couple of theorems that I wanted to prove. So I thought, would it be nice if they responded to exactly the same proof strategy? You know, state the goal, try this strategy, which of course is suitably parameterized, but you don't have to give it the parameters. The goal itself will be the parameter for the strategy. And then, wouldn't it be nice if it'll respond? If both of them will respond to the same strategy? Well, I tried it, and it worked, so that was very nice. So I went along in a couple of hours to McCarthy. I thought, this time I really am going to have a conversation. So I said to John, let me show you this problem I've got on substitution, because I want to show you how my proof method works on it. And so I showed him the first problem, and the strategy worked a dream, so he said, and then he said, being a rather quick thinker, gee, I wonder if it would work on this. And I said, what problem would that be? So he wrote down his problem. Turned out to be my second problem. So I said, I don't know, let's see. And luckily it still did work. And so McCarthy grunted for the second time, and that was very satisfying for me. But in fact, it was one of the things that gave me courage to go on with this notion of how you compose strategies and so on. Now, I worked with so many excellent people that I'm never going to be able to mention them all, but at Stanford it was Malcolm Newey and Richard Weyrauch, And when I arrived in Edinburgh, with a group of people, first of all Malcolm Newey and Chris Wadsworth, and then, no, Malcolm Newey and Lockwood Morris, and then Chris Wadsworth, who you've heard was a real expert in the lambda calculus, came to work in building a theorem prover with, or a machine-assisted prover with us, and Michael Gordon. And we set to work on trying to do it properly with a way of expressing these strategies in as general a fashion as we could. We initially thought we should have a special language for expressing strategies. Lockwood Morris showed us that all you needed was a sufficiently powerful functional programming language. Now that was actually a great step, because we had thought this was a very special application. But what it wasn't really. What it was a difficult application. And it needed the right kind of language to run it. Well, what was the right kind of language? It was actually quite a demanding language. It would have first-order functions, it would have second-order functions. It turned out that strategies were second-order functions, but there had to be ways of composing strategies, and they were third-order functions. And you got quite naturally up the functional hierarchy, just to express very natural things, the composition of strategies. But as well as all that, it had to have imperative features, so it wasn't going to be your favorite pure functional language with no state, because all the time you were processing or amending or updating a state, which was the state of the proof so far. So it had to have imperatives in it. And that is how I was lucky enough to actually be stimulated by a real application into designing a language which worked for it. And it was such a difficult application that it turned into a general purpose language, which is now quite widely used, the ML language. And so there were two products of that, and this is what I mean by stumbling. There were actually two products of this whole exercise. One was that we generated a programming language within which we could enshrine a proof methodology, which now is used quite a lot. But the second was that using that methodology, Michael Gordon was able to begin to verify hardware, the correctness of hardware. Hardware is much easier than software to verify. And so he did exactly the right thing, chose hardware, which is sort of finite apart from anything else. And it's rather easy to express a piece of hardware, relatively simple kind. Of course, it would be huge, but nevertheless, easy to express it. And it turned out, as Mike said rightly, that he could throw away 99% of our logic and just use the simplification mechanism, which we had actually taken some care on making it efficient. And that would do proofs in hardware. So actually, the progress in verifying hardware, which is now done by Intel, using Mike Gordon's work, is one of the stumblings that worked out quite well for this whole approach. So this is one kind of verification, if you like, not so much what the formalism for assertions is or whatever, but the methodology for machine-assisted reasoning. There's one particular story I wanted to tell, but I've forgotten what it is. Maybe it'll come to me later. So that's something along the lines of the first thread. I wanted to go on to semantics now, because I think there's some interesting stories to tell there about stumbling. In languages, I actually, while I was still at City, but that was in before '68, I went along to Strachey to find out what CPL was, because a friend of mine at City now wanted to implement it. Of course, it turned out to be such a moving target that we couldn't really do that. But it was meeting Strachey and finding out about CPL, and then meeting through Mervyn Pragnell's group, which Joe has mentioned, meeting Peter Landin there, and also meeting Rod Burstall. I forget in which order, but from Rod Burstall I learned about POP2, which I think was a very splendid stage in the development of functionally oriented languages. And Peter Landin, who I will remember giving a superb lectures on, or series of lectures on the semantics of Elbow 68, which has been described by Joe Stoy, or rather, Strachey's description of it was described, I forget. But anyway, I remember Peter telling us what he thought the semantics might mean on the blackboard for about 6 lectures, 3 or 6 lectures, I can't remember. But that was absolutely fine for me. So I got interested in language design there. As I've already said, I got fascinated by Scott's models while I was at Swansea, and I used Scott's logic for his hierarchy of domains in implementing a theorem prover, or a machine-assisted reasoning. But the other thing that happened to me, and this, I think, will need to cut myself short. What time do I have to stop?
About 5 to.
About 5 to. Oh, that's fine. Good.
If you could leave 5 minutes for questions.
I will do that. Yes, yes. The other thing that I was doing at Stanford was trying to understand concurrency. I can't remember quite how it happened, but I don't think I knew about Carl Adam Petrie's work, although that was a grave omission. But I certainly knew that we had to understand concurrent computing, and I knew automata theory, and I knew that the two things didn't marry very well. And I knew, therefore, that we had to find some way in which different automata would communicate with each other. So this automaton has a transition. This automaton has a transition. They will be said to communicate if this one can't do its transition without this one doing its transition. It's as simple as that. That's not in classical automata theory. It could have been studied there, but it wasn't, as far as I could see. Had I but known it, of course, that's what Petrie was doing in his Petrie net. Although you don't see it very clearly there, because a Petrie net is rather difficult to decompose. It's a large and actually very friendly object for designing certain kinds of process. But it's not a structural thing. So with the education in structure that comes from Strachey, Scott domains, and so on, and with the intuition that comes from automata, that transition is important, we then want to put the two together. So naturally, I got very excited about, is there a Scott domain which expresses processes, interactive processes? Now what worried me is that if you've got a lot of processes trying to communicate with each other in this way of synchronizing their transitions, actually sending messages to each other or synchronizing, that actually it's not determined what will happen. It's non-deterministic. Now, one of the things that wasn't explicitly present, I don't know whether it's any who had thought about it, but there wasn't a treatment of non-determinism in Scott's domains. And I thought that there ought to be, because I could write down an equation, which I won't bother to write down, but I could write down a domain equation which expressed the domain of interactive processes of a certain kind, but only if I had the ability to express non-determinism. Now, eventually, to cut the story short, the power domain was discovered by Gordon Plotkin. It's simply the domain whose elements are the sets of elements of a given domain. But it doesn't behave terribly nicely. That is, in Joe Stoy's words, the basis of this domain eluded me completely. It took Gordon Plotkin to come along and discover, I think probably prompted by my wish to use the thing, that actually, if you did this in the right way and talked about the finite elements only, rather than talking about all elements, then it worked out beautifully. You could construct the basis and you would have the power domain. Interestingly enough, the power domain turned out to be, I think, Paul Taylor will probably correct me, but it's a Pieterist topology from 1913, something like that. But never mind, for us, it was certainly a new and important concept. So I designed a domain of processes, At that time, Kahn, who is now scientific director in INRIA in Paris, was visiting Stanford, and his supervisor was Bob Floyd, but Kahn couldn't understand Bob Floyd. He was thinking hard about processes, deterministic processes, and how to link them up. And it turned out that this kind of domain was what he lighted on. Not the non-deterministic kind that I was rather bemused with, but the deterministic kind. So Kahn McQueen, what are they called, string processes or something, where the things that connect different processors are streams of data. This turns out to be a wonderful application of Scott domain theory. And in fact, of course, you can strip it of its domain theoretic connotations, and so that it can be universally understood. But Kahn McQueen came out, I think, indirectly of the Scott Strachey approach to semantics. So that was an exciting thing, and I was, I think, a part of that piece of stumbling. Well, that's as far as I want to take processes. I would like to say a little bit more about language design, because I got very much involved with doing, as it were, an engineering standard, semantics, for the programming language ML, which became standard ML in about 1990, I think. And some of the things that led up to that were very interesting. First of all, one of the things that ML had to have, because it was going to need to be very dependable, because it was going to be what you believed in when you did mechanical proof of the machine, because it was going to run your theorem prover or your dialog with you, that was going to have to be completely rigorous. It turned out that the type system in ML had also to be really quite sophisticated, because it had to handle imperatives, and we needed a kind of polymorphism, going back to Christopher Strachey, parametric polymorphism. And so to get the types right there, and to get the type discipline demonstrably sound with respect to the semantics was terribly important. Now that was driven by the need for a robust language within which to do mechanical proof. Because if you don't do mechanical proof in a robust language, then you're building your wonderful houses on sand. In fact, you do that every time. You use an untrustworthy programming language. But particularly if you're doing mechanical proofs, you really want a trustworthy language. So that's where, and I didn't know as much as I should about the work of Roger Hindley and going back to Curry on types and the lambda calculus, but that all came in. We managed to write the first semantics of ML in using Wadsworth continuations in Scott Strachey semantics. We managed to prove that the type checker was sound against that semantics. I think what is very interesting to me is that when we came to make the language, as it were, to export it, or to make it of engineering standard, call it standard ML so that nobody should come along and standardize it, which actually turned out to be quite useful. We did. We standardized it ourselves. But anyway, we moved from Scott Strachey semantics to what Kahn called natural semantics, which was more like, closer to the SECD machine, actually an inference system for evaluation. And I think we did this because we needed to interact with the implementers while we were designing the language. And if you get too abstract, then you can't work easily with implementers. So the design of that language, which took a long time, and the design of the semantics, those three things, the design and the semantics and the implementation, went hand in hand. And I think the reason that we used an inferential or operational semantics was because it was an easier vehicle for sort of cohering the whole effort. So I really have this question about denotational semantics, that it seems to me like a place where you perhaps can sort out your ideas quite well. In fact, the Scott-Strachey discipline of using domain equations, what are your domains going to be, that is one of the biggest helps in designing a language, and that actually writing the semantics in the formalism for denotational semantics, for some reason, is not so helpful for certain purposes as other kinds of semantics. So, whether this is true or not, it's part of the business of that we hone or learn our concepts by trying to do things on realistic objects, whether they're languages or whether they're actual programs. Well, I'm going to stop in about 2 minutes. I couldn't really stop without saying what one of the highlights of my stumbling career was, which was interacting with Tony Hoare on concurrency, and because we both worked on different aspects of communicating processes at pretty much the same time, and I think we had different motives. Mine was to try and get an algebraic theory for these things. Tony's perhaps was too, but I think also he had the idea of a programming language which could be really simple and well understood. And it's always been a puzzle to me that we ended up by doing things which were tantalizingly similar without being the same. His CSP and my CCS are actually not too far apart, but however hard you try to identify them with each other, it's still not quite the same. But that process of comparing these two, discussing them, was for me very important. The very fact that these two things couldn't be identified seemed to indicate that they were part of some larger space which needs to be understood. And that larger space is something I think that we're still working at. Of course, the goalposts keep changing. Then the stimulus was to understand distributed computing. Now the stimulus is to understand mobile computing and the internet, and actually to be able to model that with appropriate algebra, whatever you like, graphical models of one kind or another. And I think this process of if you can call it a process, of trying to understand what computing processes are, particularly concurrent processes, is one of the biggest ongoing challenges to the theoretical community. So I hope this hasn't been too incoherent. It's really trying to be, to exhibit a sort of tension between formality on the one hand and arriving at or stumbling across concepts on the other. And I was lucky to be part of some of this. So without trying to wind it all up, I'll just stop here. If there are any questions.
Thank you very much. I'm wondering about the semantics of your orange threads, which don't appear to go all the way from City to Cambridge.
Well, no, they don't. I mean, oh, sorry, these threads are, those lines actually represent my involvement with life. This thing I stopped doing around about there. Yeah. Other people didn't stop doing it.
But you leave SL, before you join it.
Sorry?
You leave, what does SL stand
No,
for?
oh, well, I was actually running in parallel here. Okay. I was not, oh, you know, in a sense. Of course, I was only, I don't want to emphasize this as applying to me. This is how it applied to me, if you like. And I was trying to tell some story about how they developed from each other as far as I was concerned. Please don't take it too seriously.
Steve Vickers, you said that domain theory and denotational semantics provide a very good way of trying to understand what the language is about. And we've seen it very successfully in the imperative and functional. Am I too quiet?
Yes.
You see, how well would you say that denotational semantics and domain theory are living up to the challenge of understanding object-oriented languages
Yes. I actually don't think very well, because I think for object-oriented, you need a sort of repertoire of concepts which may well have been handled well denotationally. I don't know that they have. And I think that in these kinds of languages we seem to have become much more concerned with the structure, with the, the entities, the objects, rather than the abstractions which lie behind them. I think that concerns have become, in some sense, very concrete with objects. So I don't know of as good an explanation from denotational semantics as there is, say, from, if you take Abadi Cardelli's book on object-oriented programming, it's very much to do with types and inheritance, and those concepts don't obviously come out of denotational semantics.
But Robin, that's equating denotational with domain theory. David Walker and others have mapped object-oriented languages into the Pi calculus and said that's got a natural algebra, and that's mapping from a non-understood language into a denotation space.
Well, I don't think it's a denotation. With respect, it's nice that it goes into Pi calculus, but I don't think that's a denotational. I don't think that's denotationally very well understood. I don't think denotational semantics has helped the understanding of that. Perhaps it will, and I know there have been attempts, and I know them in some detail. But one of the, I think it's in some sense excruciating that there's something very concrete there which doesn't yield to the kind of abstraction that denotational semantics wants to make. So yes, you can go from objects to the Pi calculus, but going further is the problem, I think.
Other questions? Robert.
Hi.
Could you say something, this is a very non-technical question, could you say something about which sort of communities or tribes you belonged to in the early days? Or was it really just individuals doing this in isolated places? And at what stage did it sort of coalesce into a community? It seems
Well,
information.
I don't think it, so to speak, if you mean this stuff, has coalesced into one community. But I've always worked in different communities. If I could take this for an example, I worked at Edinburgh, particularly with the people I mentioned, 4 or 5 people on this stuff. And then they left. And Chris Wadsworth went and worked for the SERC, and Mike Gordon went to Cambridge and did hardware verification. I went on and did other things and worked with other communities. So I think probably, like most of us, we all moved from one community to another. But I think there were communities, there was certainly, for me, a community working here, and certainly on the semantics of ML, there was another community, which was quite a distributed one in many ways, and about 15 people eventually. And then working on process algebra, that's been another community. So those, they overlap coincidentally, I think, but they never cohered into one.
One final question. Richard, did you have your hand up?
Richard Bourne at Queen Mary College. I'm not sure this is, I'll try and put it. You said something to which I wholeheartedly concur as one of nature's natural implementers. You said it's not worth, I am one of nature's natural implementers, not
Yes.
You said it's not worth being too abstract when talking to implementers. Is this because things like domain theory seem to us implementers to be answering questions that don't need answering? That we're natural constructivists, and you people who work on denotational semantics lean a bit too far platonically for us.
Maybe. That's awfully valuable, all that you said. So
Oh yes.
I'm not going to agree with it all, because we'll both be in trouble. But I had an experience. I think ML was too complicated a language, by the way. But I did have the experience of going to Harlequin twice on my bike while I was on sabbatical in Cambridge in 1990, and that was all I had to do in order for them to implement it correctly. They really did implement it correctly through that semantics, and it's because each evaluation rule, each of the 196 rules that we have there, corresponds to a bit of code. Now you could say the same thing for each equation in a denotational description, to some extent, could correspond to a piece of code. But there, it's slightly less direct. And I think the fact that each of these rules, both the type-checking rules, by the way, and the evaluation rules, corresponded very directly to code. So I think it was much less frightening for implementers. They didn't have to, get up onto that abstract pedestal. I'm not saying this is a bad thing about denotational semantics. I'm just saying that it happens to be true, I think.
Could we break there and grab Robin afterwards for further questions and thank him again?